Another example of conditional independence comes when you, right, let's say you toss a pair of dice, right, pair now, right. This I am not going to work out in great detail, I am going to let you do it yourself, right. Let us say define this event A as the event that what, the smaller number is exactly equal to 3, and then B as, define it as a larger number is exactly equal to 6, and then C as the event that the smaller is less than or equal to 3 and the larger is greater than equal to 4. This comma always, by the way, is going to mean and from now on, right. The smaller number is less than 3, the larger number is greater than equal to 4. Now I'm not going to I don't, let's see how much time we have to, I don't want to spend more than 2-3 minutes on this, right. So it turns out that A and B are conditionally independent given C. How do I prove this? I have to calculate P of A B given C, P of A given C, P of B given C, and do the multiplication, right. So I need to do all those calculations, right, but they are not independent, but A and B are not independent. They are conditionally independent given C, but they are not independent. Less than equal to 3 the large. So how would you'd have to actually write out all combinations which would give you this, and this is a compound space, and you're assuming whenever you see pair of dice that each, right, now the sample space is 36 points and each point is equally likely, right, that is the standard assumption that the dice are independent, each die is independent of the other, and that gives you the 1 by 36, right. So this P of C is half, that is anyway there, right. What I meant to say was P of A C will be equal to 3 times 2 by 36, this will be equal to, I meant to say this, in wanting to say this I said that, right. The AC and BC have the same probability, you're right that this is not true, but what I meant to say was if A is a subset of C and somebody asks you to find P of A given C, you can just easily find it as PA by PC, that is basically what I wanted to say here, but this is not true, right, you are absolutely right, and that in this particular case A is not a subset of C here. But I just want to point out that BC and AC have the same probability, right, you need all of these things, right, and you have to show that, I am not going to do it any more than this, show that PAB given C is what, will be A given C multiplied by, so in this case it is exactly equal to 4 by 36. But P of AB is not equal to P of A into, so I just I am not going to spend more time, I do not have, right, any more time to spend on this, but right, but this is what I want you to show by yourselves, you are perfectly capable of doing it, right. So you would require all of these things, right. What I meant to say, in fact, what is a subset of something? I guess AB is a subset of C. Is it true that AB is a subset of C? A intersection B is a subset of C. Is that right? Yes. Yeah, that's what I wanted to say, right. AB is a subset of C, not A is not, right. So if I wanted to, well, I just replace this note with an if, right. This is perfectly okay. So here AB is a subset of C. This is, I am doing all this and spending half the lecture on this just to, right, strengthen your intuition, right, in this important concept, right. You can have conditional independence which is different from absolute independence, right, and we have seen 2 examples of that, right. Okay. Say you have m black balls plus n white balls in some. This is unfortunately here I have to do this for drawing. You need to consider this kind of situation. You don't have a choice, right? So if you have a collection of m black balls, so what did I say, m black balls and n white balls, and you're drawing, let's say, 2 balls. Let's say 2 balls. This is a standard example where you're closing your eyes and pulling out 2 balls, right? They all feel alike, right? You can pick out any 2 of them. So in this kind of a situation, what is it that you can, what kind of outputs can you get? You can either get 2 white, 2 black, assuming that m and n are both greater than 2, right? Assuming both are greater than 2, right? You can get 2 white, 2 black, or one white and 1 black. You can also look at, right, drawing sequentially. It turns out that if the overall, the aggregate probability, for example, of drawing 1 white and 1 black, it's the same, right, no matter how you calculate it. Whether you calculate it as first ball is white, second ball is black, or first ball is black, second ball is white. You can do it like that, or you can say I'm going to pull out both balls and use combinatorics to write out that probability, right? So it turns out, for example, here the probability of one black plus 1 white here, there is no concept of which is first and which is second. You're just pulling them out together, right? So this is going to be, the denominator of this is always m plus n choose 2. Why did I get this n plus n choose 2? That this is a notation we are going to use for combinations now, right? Not the capital C thing, right? This is the standard notation which is used for what? Choosing n objects out of, sorry, r objects out of n, regardless of ordering, right? So what is this? This binomial, this coefficient equal to this combinatorial coefficient. This is n factorial divided by r factorial divided by n minus r factorial. So how do you write this? This is the internationally accepted standard, right? No C, capital C stuff. You write, you put 2 brackets like that, somewhat elongated, right? You put the n on top, you put the r at the bottom. Please stick to this, right? And transform all your earlier, I'm sure all of you have seen combinatorics at some point in the past, right? But this, have you seen this notation specifically? Yes, you have. Those of you who have not seen this particular notation, please note it. And factorial also, we'll just use the exclamation mark, right? So here this m plus n choose 2 is what the number of combinations you can have. The total number of combinations of choose 2 is just 2, the number of ways of choosing 2 balls out of m plus n, right? So here what are we going to put in the numerator? It's m choose 1 times n choose 1. And these numbers can be generalized. I can have, right, I need not have just 1 and 1 here. I can obviously have even the 2 and 0, for example, is going to be m choose 2 divided by, there's no n choose 0, right? And anything choose 0 is always 1. All of you all know that, right? So that n choose r is always equal to what? N choose n minus r. These are all very, please go brush up your combinatorics just to make sure that you're completely comfortable with these things, right? Etc. So you can write out the probability of, right, either choosing 2 black balls or 2 white balls, or this 1 black ball plus 1 white ball using this. Now the interesting point I want to make is, right, in this business of this is called drawing without replacement. You're not putting back anything, you're just taking it out. So the aggregate drawing of 1 white ball plus 1 black ball, right, the probability of that doesn't depend on the order, right? And it doesn't, whether you look at first ball, as I just said some minutes back, first ball white, second ball black, and then you also look at first ball white, first ball black, second ball white. You add them up, you will get exactly this number, right? And it turns out, in this case, the, right. One more interesting point which we can make is this: what is the probability of the first ball itself being black? It's m by m plus n, right. This I don't think anybody will complain, right. This is in fact a simple way of simulating what, a biased coin, if you want, right. If you think that you can't manufacture a coin that will land with heads with probability 1 by 10 or something, all you have to do is pick the same, that many white balls and black balls and simulate this, right. But what is interesting is that this same number is also the probability that any, right, how many balls can you draw? You cannot m plus n balls, right. So you can keep on drawing balls. What, at any point the probability of drawing a black ball will be that n by n plus n, as long as, right, yeah, I mean in fact that is true, as long as there are balls in the box that you can draw, right. The second ball being black, that is regardless of the first ball, you don't care, right. If you draw 2 balls, you don't care about the first one. Look at the probability second ball is black, that also will be m plus n, in fact, right. So here we don't care about the first ball. You can easily show this in the way that we did the earlier calculation, right. You can condition on the first ball being either white or black, right. So how do you get, assuming that m and n are both greater than 2, right. So you can have first white, second black, or first black, second black, right, and if you add it you will get this. No, they are not. We are drawing. We are drawing. We are saying we are drawn at random without replacement, right? Actually, it's true even with replacement. That's the interesting thing, right? Even if you put it back, you get the same m by m plus n. But even without replacement, you still get m by m plus n.